Hello everyone, welcome to this NPTEL course on Advanced Prestress Concrete Design. We are entering into the week 3 of this course. In this lecture, we are going to talk about the response of prestress concrete members under axial loads, that includes both compression and tension. The expected learning outcomes are the student will be able to understand the mechanism of behavior of prestress concrete members under axial load, and the student, after going through the video, he or she should be able to develop the entire axial load versus deformation behavior of a prestress concrete sections, and we will look at if you change the reinforcement detail how the axial load deformation response is going to change, right. And the student should also be able to understand the effect of time dependent losses in the axial behavior, right. So, the members in general, concrete members or prestress concrete members, they are subjected to pure axial loads only in an idealized condition. So, what is the meaning of that? So, they are always subjected to some bending or shear along with some axial forces, right. So, it is an idealization. Now, the members that are commonly subjected to axial compression or tension in following cases, some of the cases in a tied arch bridge, there may be members that will be subjected to pure axial load. Columns in bridges and buildings is one example, piles is another example where we may have axial load, and hangars and concrete truss elements. So, a lot of industrial structures, typically when we say truss, typically we assume that it will be a steel truss, right. But however, there are a lot of industrial structures that have been built with concrete truss elements as well. So, these are the scenarios where you will have members subjected to pure axial loads, right. Now, these are some of the examples. You can see there is a precast RC truss. So, of course, you can say that you have to design the element in such a way that under tension they are not going to crack, and you are also going to put some reinforcement to make sure that the crack widths are also going to be limited under service loads in case of a precast RC truss system. And in hangers, you can also say that sometimes if the slabs are hanged from these elements, when you have a load, then this member will be subjected to axial load. So, this is another example where you have concrete elements subjected to axial load. Now, this is one more very interesting case of a Samtel Color Limited. This you can see the nice truss, roof truss element which is made of reinforced concrete, actually it is post tension with pre-stressing steel. So, you can see that the tie elements are usually tensioned, so that they are put in compression under, always they are going to be in compression under service loads. Now, when we talk about axial behavior, we need to also understand what are the compatibility conditions in different systems. Now, when you have a reinforced concrete system, while you are casting, you will make sure that the strain in the concrete is equal to strain in the steel, where epsilon s is nothing but strain in steel, right. And similarly, epsilon p, here you can see here the strain in the pre-stressing strand, which is a reinforcing element that is used in pre-stressed elements. Now, in case of a strain in the pre-stressing strand, it is not going to be exactly same. Okay. So, pre-stressing steel strain epsilon p will always be equal to epsilon c plus delta epsilon p, which is nothing but the initial strain that we lock due to pre-stress, due to pre-stressing. So, this delta epsilon p will always be there, which is nothing but your initial pre-stressing that we are getting. Now, how do we calculate this initial pre-stressing strain delta epsilon p? If we call that as, this is a differential strain, right. So, this is basically the initial pre-stress that we have divided by EP, which is the modulus of elasticity. Typically, we say that as initial pre-stress. So, typically we stretch them to, as you know, 70% or 75% of your ultimate strength. So, you know the value and then you can divide by elastic modulus of the steel to get your initial strain that what you are putting on. Now, there may be differences in this initial conditions of concrete strain. For example, when you do the pre-tension concrete, as we have discussed in the introductory module, okay, in pre-tension concrete, we stretch the cable and then we pour concrete around that cable and there is no duct in the pre-tension system, and then the transfer of prestress happens when you actually cut the strand, right. So, at that time both of them they undergo the same strain when you transfer the stress. So, the initial strain at the time of transfer is going to be 0 in pre-tension concrete. However, in post-tension concrete you can see that the concrete element may be cast somewhere else, right, and the stressing will be happening at a later point of time, or maybe initial stretching, some low level of stressing may be done initially, but the majority of the part of the stressing will be done at a later point of time. So, that limited pre-stressing typically we do while we erect the members so that they do not undergo cracking. So, in case of a post-tension system, because they may be supported and it will be when you are doing the pre-stressing, already the concrete element will be subjected to some self load, self weight, okay. Self weight will always be there, and depending upon how you support this post-tension concrete system, your strain in the concrete at the level of your steel may not be 0. There will be some initial strain that will be there, that we need to account for them if you want to do an accurate calculations, right. So, this is mostly it will come from the self weight of the system, or maybe some other superimposed loads that are acting on the system while you do the pre-stress, that will induce some initial strain that we need to consider in our calculation. So, the point is, in post-tension concrete, while you transfer the pre-stress, the strain at the level of steel may not be 0, it may be some low values of strains are possible. Right. Now, let us look at the response at different stages. Now, let us say that I am dealing with a post-tension cross section element like this, and I am applying an initial pre-stressing force of let us say P0. Or we are looking at now how the member will behave under axial loads. Now, when I transfer this pre-stress without any external load, so that is what here we have no external loads, then how do I calculate the stresses? Let us say that this is some steel, okay, which is let us say AP, right. So, to calculate the stress, axial stress in the concrete, now when there is no steel, we can directly say the applied force is P0 and the area of the concrete is going to be AC. So, P0 by AC will give me this stress. But typically in a concrete element, we will always have some reinforcement, right. So, when you apply the load, the reinforcement also is taking some stress, right. So, then what we have to calculate is, we have to calculate a transformed section. So, you know how to calculate the transformed section. Transformed section is actually taken as AC plus ES by EC into AS, right. If AS is your reinforcing steel, or in this case it is AP, okay, AP or AS, whatever that you have, that amount of pre-stressing steel, and we know the elastic modulus of concrete, we know the elastic modulus of pre-stressing steel. So, if you take the modular ratio multiplied by the AS will give you the additional equivalent concrete area that is given by the steel. So, this is the way that we calculate your transformed area. Then the stress is going to be P0 divided by AT, which is not AC, it is AT whenever you have a reinforcing steel. Now, we can also calculate the stresses under service with the external loads. Now, see, in a pre-stress element, you have already done the pre-stress with P0, okay. In addition to that, you are also subjecting an external load P, in this case it is a tension load, okay, it is a tension load. Then how do I calculate these stresses? It is very simple, you can use the principle of superposition, and P0 by AC is the initial stress due to pre-stress. Then the next one is due to external loads, okay. So, this is when you do not have any reinforcement, somehow you are creating, let us say that the pre-stress, then you have pre-stress effect, then we know that the pre-stress sign convention we always take compression as negative and tension as positive. So, in this case it is going to be negative P naught by AC plus P by AC, where P is your external load, right. The second case, when you have steel, of course, you need to put P minus P naught by AT, because compression is always going to be considered as negative in our sign conventions. So, negative P naught by AT is the stress induced to pre-stress. Then the external load is being resisted by a transformed section, which is AT. So, this is the thing. So, now in this case here it is in tension. So, the sign convention for this case it will become plus, but you can also have axial compression. In that case the effect of P will be negative, right. So, the stress you have to put negative here. So, in this way we can calculate the stresses under service loads. So, in general, when you are designing an axial element, we need to make sure that under service condition the concrete should not crack, okay, or in other words the stress in the concrete should be always less than FCR, which is the tensile strength of the concrete that is given in your IS code. So, that we know it is a pure material property, depending upon the grade of concrete your tensile strength of the concrete will change. Then accordingly you have to make sure that the stress under service is not going to exceed the allowable stresses in the service condition. Okay. Now, let us look at, we have seen how to calculate the stresses under service condition. Now, let us look at how do you calculate the ultimate capacity. Again you see here, this is again a tension load that is applied. Okay. Now, this is the same cross section that we have, and we need to calculate how much PU this particular member will be taking. So, you can see here, once I start increasing this PU, some level you will have axial tension here. So, you will have this kind of cracking. So, at the cracked location, for example, if you look at it here, it is only the steel that is actually resisting the applied load. So, the ultimate tensile strength PUR can be calculated as per the clause 23.3 given in IS 1343, which says that you need to take only steel, because the concrete has already cracked, right. So, we need to take only steel contributions in the ultimate strength calculations, and we know that the maximum strength it is taken is FPK, which is a characteristic strength of the pre-stressing steel. Stress multiplied by the area will give me the force or the strength, that again I need to apply some material safety factor, which is 0.87. So, in this way, when there is no non-pre-stressed steel reinforcement, okay, in the absence, that means you have only pre-stressing steel, then this is the equation, and with the assumption that at the cracked location it is only the steel that is resisting the entire applied load. So, the ultimate strength is going to be 0.87 into FPK into AP. Now, you also have a section like this, both AP and AS. Okay. So, in case of an axial load, it does not matter where you put your reinforcement, because you are applying an axial compression. So, the section will be subjected to the same strain, right. So, you can have both AP and AS, or only AP or only AS, right. So, in case you have both of them, then how do you calculate the strength of the section? Again the same process. Now, the maximum strength of a non-pre-stressed steel or a normal mild steel is 0.87 Fi into AS, and then you have, this is from pre-stressing steel. So, this is from pre-stressing steel, this is from a regular non-pre-stressed steel, right. So, we add both of them, that is the total resistance that is offered. Now, what is the yield stress? We all know that yield stress corresponds to 0.2% of the proof stress for non-pre-stressed reinforcement, and for pre-stressing steel also it is equivalent to 0.87 FPK. So, that is your yield strength. Okay. So, FPK is your characteristic strength, and we know that it is equal to 1860 megapascal typically for a pre-stressing strand, right. So, in this way we can calculate the ultimate capacity under axial tension. Again, in axial tension you assume that the concrete to be cracked, it is only the steel it is taking all the load. Now, let us look at how to understand the entire full behavior. So, what is the meaning of full behavior? I want to establish for a particular member how the load versus the deformation of a section is going to be. I want to establish this load deformation curve. Okay. So, for that how do we do it? For example, this is your load that what I am applying for this member. Let us say that this member is having, let us say 1 meter for 1 meter, which is equal to 1000 millimeter if you talk in terms of. So, let us say this, and these are the nomenclature that what we are going to follow. For a typical cross section area, if we call that as A, it includes everything. When we say AC, it is only the concrete area, and AS includes only the non-pre-stressed steel, regular mild steel or deformed steel, which is not pre-stressed, and AP corresponds to the area of pre-stressing steel, right. Now, for this load, let us say that in this case, for example, let us say this is equal to P, okay, the applied load. Now, what is the load that is resisted? You know, if I start integrating, so the entire cross section will be subjected to same strain, right. So, if I take a cross section, and this cross section will be subjected to same strain, okay, because it is an axial load. So, let us say this is epsilon C, okay, and this is the cross section, this is the strain profile. So, this is the strain profile. So, what are the individual area? Now, a section can have concrete, non-pre-stressed steel, which is AS, then pre-stressed steel AP. Now, each one of them are subjected to the same level of strain, right, when you apply the load. So, the stress multiplied by the corresponding area, when I integrate it, I will get my load contribution from concrete. So, this is going to be your PC, and this the stress in the steel multiplied by the area of the steel, when you integrate it for when you have multiple layers, then you will get the contribution of your non-pre-stressed steel PS. Then the pre-stressed steel stress multiplied by its area will give me the load contribution from a pre-stressing steel PP. So, the total load resistance is going to be the resistance offered by concrete plus the resistance offered by steel plus the resistance offered by pre-stressing steel. So, this is what, when you integrate this, then you get FC into AC plus FS into AS plus FP into AP. Now, depending upon you know, if the material is going to be linear approximation, then I know that Young's modulus times the strain will give me the stress. So, you can do this linear approximation for a given value of strain. If your load levels are less, if you assume that the entire system is going to be in elastic regime, then we can use simple constitutive equation like this. Stress is nothing but elastic modulus multiplied by strain, then you can get your stress quickly, right. So, in this way we can get your Now, let us look at how to do the analysis at ultimate. So, this is one, you know, we go back, and this is the way that we generate for load resistance. Okay. This is purely from equilibrium condition, right. Now, what are the compatibility condition here? That is what we discussed. For a normal RC section, we say that epsilon C will be equal to epsilon S, and for a pre-stressed section, we say that epsilon C will be equal to epsilon pre-stressed steel. If you say it is going to be epsilon C plus delta epsilon P, and we know that this is your initial strain that we have applied to pre-stressing steel. So, this is the strain compatibility. So, this is the strain compatibility relationship that we are going to use. Okay, right. Now, let us quickly understand how the IS code is, before we get into the full axial load versus deformation behavior. Let us now look at how the IS code is actually calculating the strength at ultimate. Okay. Now, if you look at this stress strain curves, which will be familiar to you, and we know what is a characteristic curve, and the characteristic curve is arrived from, you know, that the maximum stress that we can take from concrete is 0.67 FCK in a characteristic curve. Again, how do we get this 0.67 FCK? typically the pure material property, the cylinder strength, but actually we use cube strength. So, cube strength, if I have to convert it into cylinder strength, I need to apply 0.8 factor, reduction factor, because cylinder will have lower strength, which is the actual true material property. We have discussed this in the introductory classes. Then again we apply some size factor, because typically we test small elements, but in reality we will have we deal with large size elements where the possibility of defects are going to be more. So, we apply the size factor of 0.85. So, 0.85 multiplied by 0.8 gives me 0.67 FCK. This is the characteristic curve that we use, right. And but for design we do not use a characteristic curve, we divide by the partial safety factor, material safety factor, and then we use only 0.447 FCK is the ultimate strength that is offered by concrete in compression. So, this is how we get your design curve. Now, we know that this concrete sections, the failure strain for pure axial compression is actually taken as 0.002, which is your epsilon Cu. So, corresponding to that 0.002 from the design curve, how much is the maximum stress that we get? Corresponding to that is this 0.447 FCK. So, we know that for resistance we need to have PC plus PS. Now, what is PC? PC is nothing but maximum stress from the design curve is 0.447 FCK multiplied by the concrete area AC plus the stress in the steel in compression, because this is for compression, right. So, this is we are taking it for compression, or we are taking it for compression, right. So, this is the capacity that we take for compression. So, now you can also have for example, if you want to do an accurate calculation. So, if you do this in terms of AG, the overall gross area, then I have to subtract the stress offered by concrete, which I have already included in AG. So, that is the reason we subtract this 0.447 FCK from the FSC when I am dealing with this AG calculation. So, we know that, right, because AG is nothing but AC plus AS, right. So, if you decouple that, you will end up with this equation. Now, what is the stress in the steel? The stress in the steel for a strain of, so this is a stress in the steel corresponding to a epsilon Cu equal to 0.002. So, that is the ultimate strain for concrete, and in axial load you know that the entire cross section will be subjected to same strain, right. So, depending upon the grade of steel here, for example, if you look at this Fe 500, right, for strain of 0.002, what is the stress that we get? We get a stress of 0.746 Fi. The yield strength may be Fi equal to 500, but at 0.002 we are getting only 74.6% of that 500. So, this is the stress that we need to use in our strength calculations for compression, right. So, then this becomes Pu naught for Fe 500 will become 0.447 FCK times AG plus 0.746 Fi minus 0.447 FCK into AS. So, as per class 39.3 of IS 456, the column actually must be designed for a minimum eccentricity of 5%. So, what does that mean? So, that is what we said in the introductory slide itself, that for pure compression or pure tension is an idealized situation, but in reality the members will always be subjected to some eccentric loading. That means a member will be subjected to axial load plus bending moment, sometimes shear also may be there. So, the code is saying that because always you cannot ensure pure axial load, you need to apply a 10% reduction. So, I take this formula, right, and I multiply this by some 0.9, right. So, then you get your equation as this point. Basically, if this will work out to be for Fe 500, you will get this as point, in fact 0.4, this should be 0.4 FCK into AC plus 0.67 Fi into AS. This is the value that we have to use it in our design for pure compression. So, this is compression. And we have already discussed in tension, it is only the steel that will take the steel. Now, what will happen to when you have pre-stressing steel, that we will discuss. So, you need to have again one more component, stress in the pre-stressing steel multiplied by AP. Now, the stress in the pre-stressing steel, there is a tricky. So, always we have seen that epsilon P will be equal to epsilon C plus delta epsilon P. Now, what is delta epsilon P? That is the initial strain that I have locked. Always pre-stressing steel will be stretched in tension. So, this will be positive, this will be negative. So, the net epsilon P that we need to calculate and we have to use, that we will see in the coming slides. Okay. So, this is for a typical how to calculate the ultimate strength in tension and compression.